This link is the link I just put in our Google Meet chat. So if you just click on that, you'll be able to type in questions. And then after you type in the question, there's a little box where you can check make anonymous. And then nobody knows. You can ask anything you'd like. Conservation of energy in circuits. Analyzing loops and electric potential. So, as we go through this, conservation and conservation laws and conservation rules can be interpreted, that phrase can be interpreted a few different ways. So just to make sure we're all on the same spot, if people talk about conservation of energy in the news, politics, social science stuff, or environmental stuff, in those cases, when they talk about conservation of energy, they usually mean like turn off lights when you leave the room, make sure you consolidate your trips in the car so you don't drive your car multiple times when maybe one trip would do it, or try taking the bus. That's what they mean in those settings when they talk about conserving resources or conservation of our resources. That's social sciences and some environmental sciences. But in the physical sciences, we mean something very different. In the physical sciences, when we talk about conservation of energy and physics and chemistry, physical science stuff, when we say conservation of energy, we mean there that you cannot create energy or destroy energy. We can change the type of energy from moving energy to an energy that's visible based on the changes in temperatures or electrical energy, things like that. But for us, we mean that total amount of energy is constant. It just changes form or changes how we see it, and how we can capture it or use it or contain it. So that's the sort of energy conservation stuff that we would talk about. And that's the sort of conservation stuff that we would talk about. So when we talk about conservation of charge, separate from conservation of energy, still a conservation deal. If we talk about conservation of charge, we're saying that, hey, these charges exist everywhere in this circuit. There are atoms that make this stuff up. Those atoms have positive charges, protons, and negative charges, electrons. And those charges exist everywhere in that circuit because there are atoms everywhere in that circuit. And so there are charges everywhere. It's not within our ability to create a charge and plop it into existence. It's not within our ability to take those charges and remove them and have them be removed from the universe. We can't do it. We can take them and change their position, change where they are, but we cannot just pop some into existence or delete them from the universe. That's just, we can't do that. We don't know how to do that. The universe might do that in other locations, but not right here, not in this circuit. Okay, and that's what I just said. And then when we talk about energy, if we talk about the energy located at different spots, or the energy per charge at different spots, at a single location, every charge would have the same energy. So if we're saying, hey, this is the spot we're going to say is 0 units of energy per charge, it doesn't matter which charge is at the location of this red probe. If we're saying this is a location of 0 energy, every charge, when it gets here, every charge is at 9 volts of electric potential. There are 9 volts, 9 joules per coulomb of energy for absolutely every charge that passes through this point. Once it's at a different spot, well, that charge would have a different amount of energy, or could have a different amount of energy. But when it's at this spot, it's got 9 volts. Every single charge at this spot, every coulomb of charge at this spot would have 9 volts of electric potential. Yeah, there we go. So as you move through a circuit, the electric potential or voltage or electromotive force would be the same at that spot, and it might change. The potential value could be different at different locations, but the electric potential at that spot is what it is. Electric potential doesn't travel or move. It's an amount at a location. Electric potential exists at a location. It doesn't, electric potential does not flow. Current flows. Electric potential is a value at a spot. All right, so bulbs use energy to make light. The energy has to come from somewhere. And when we're doing that in circuits, the light energy comes from the electric potential from the charges. It doesn't take the charges, it takes energy from charges. So if we think about those charges, like electrons, they gain energy from chemicals in the battery, right? So if we're using batteries and charging your phone, and we're talking about the energy that your screen has on your phone, the screen, that light, comes from energy from the charges moving, and those charges get their energy to move. Those charges get their electric potential from the chemicals in the battery that you charged. So the chemicals in the battery give the charges energy. Those charges can then create light energy on your screen. And sometimes, if that thing runs for a while, you'll notice that it makes light energy and some thermal energy. You'll notice a change in temperature of your phone or of whatever device you're using that has electricity running through, that has a current running through. So it's, in those cases with a battery, we're talking about chemical energy becoming electric potential, or electrical energy per charge. Electric potential is energy per charge. And then that can become light energy or thermal energy with temperature changes, or it can become some other sort of mechanical energy like a motor spinning, things like that. And then remember, we'll talk about energy per charge. These things, these phrases are things that we're kind of adding, right? Initially, we spoke just about current and flow. Now we've added electric potential. Electric potential. And remember, electric potential is energy per charge, or electric potential energy per coulomb of charge. And a coulomb of charge is like an amount of charge. It's like saying we've got a dozen charges. It's not a dozen, but it's a number. It's like saying we have an amount of charge, the electric potential energy per amount of charge. And that should be a little bit of review. Throwing in conservation there is a little bit new. Bulbs use energy, they give it off. The energy comes from the charges. The energy comes from the battery, or the electric potential of the battery gives those charges energy. Electric potential is energy per charge. It's kind of like energy per electron. It's not really, because an electron does not have 1 coulomb of charge. But as a mental model, trying to think about what's going on, it can be thought of as a volt of electric potential can be thought of as energy per charge or energy per electron. That's a useful mental model. The number isn't going to be 1 to 1 to 1, like 1 volt doesn't mean 1 joule of energy per 1 electron. It's not 1, 1, 1 there. The numbers are different. But we can say that a volt of electric potential does give energy to each charge. And I'm doing this, that's like, I'm thinking fraction, right? Joules per coulomb with a little fraction line. And then when we're looking at this, what's brightest? Bulb 1, bulb 2, bulb 3. Let's see, I don't remember. Oh, we used to do this with a slightly different thing. Okay, so that's going through talking about most of what we've got. I think that's probably good for the slideshow. I think the next thing that will be helpful is if we just go right into the Google Form.